Welcome to our presentation on the application of Bernoulli equation as a part of our hydraulic lab sessions. This experiment is curious for understanding one of the most fundamental principles in fluid mechanics, Bernoulli theorem. It helps us analyze how fluid pressure, velocity, and elevation interact to transform as a flow fluid those different pipe of sections. Today we will walk you through how this theory was tested in the laboratory setting using a Bernoulli demonstration unit. Let's now move on to the course objective and learning outcome. And let's go. Course overview and objective. Learning objective. To verify experiment the value of Bernoulli theorem for the fluid flow under the steady condition. Second, learning outcome. Student will be able to identify Bernoulli equation, conduct relate laboratory experiment, and analyze and interpret the obtained data. Let's go to the theoretical background. Theoretical background. Bernoulli equation is based on the conservation of energy for a fluid steady increments a non-physical fluid. It combines three components: pressure head, which is rho P over rho G, velocity head V square over 2G, and elevation head is Z. These three terms add up to the total head or total energy of the fluid. In case we both point at the same elevation, the question is simply we can measure the pressure head using a probe that helps the fluid locally, and we calculate flow, velocity, and volume.
Before we start the experiment, we need to know the apparatus of this experiment. Let's go. Firstly, hydraulic tank. Second, stopwatch to take reading Q. Third, ruler to take reading Bernoulli apparatus. Fourth, Bernoulli apparatus. 5, stopper. And lastly, button switch on off for hydraulic bench. That's all.
So now that we know all the apparatus, we can start the hydraulic bench by pushing the start button, and then we can open the gate valve to let the water flow through the apparatus. So this is when the gate is open and water will start flow through the Bernoulli apparatus. Make sure that the water will flow and all the bubble inside the tube will go outside the tube. And then you can close the gate valve. After that, you need to make sure all the water in the tube are in the same level through tube number 1 to number 6. And it is already given that the diameter in all the tube, and the diameter is in unit millimeter. The next part is going to be how we going to collect the data from the apparatus.
Okay, let's go. After that, you need to open the valve and make sure to adjust carefully the inflow valve and outflow valve to get the flow with high and low manometer level, and record the scale reading of each manometer level at all 6 points. Okay, so after that you need to close the water stopper. After that, we need to record the time with stopwatch. Okay, by using stopwatch, you need to record the time with the volume that already being set. For example, the volume is 0.002 for the first set, and take the record into the table. After that, repeat the step with different flow rate and collect 3 sets of volume and time reading to calculate average flow rate.
Next is for the sample and calculation. We are going to use the data from test 1, which is for the cross section. The formula is pi r squared, and the answer is 4.9087 times 10 to the power of -4. For the velocity calculation, we are going to use formula Q over A, which is the answer is 0.0701 meter per second. And the velocity head calculation, we are going to use the formula V squared over 2G, and the answer is 0.505 times 10 power of -3 in meters. And the total head calculation is the velocity head calculation plus the head of manometer from the Bernoulli apparatus, and the answer is 0.2003 meters. And the figure below shows how the principle of Bernoulli works. So this is all the tests that we took. We have test 1, test 2 and test 3, and this is all the result that we get from the calculation that we use from the sample of the calculation.
Discussion of result. Verification of Bernoulli principle. The experiment successfully demonstrated that when the area of flow decreased, flow velocity increased and pressure decreased. This was evident in the venturimeter where the head was higher at the narrower tube section. Real vs ideal fluid. Water is not an ideal fluid as shown by the difference between theoretical and observed values. The final column water head was not equal to the starting values, indicating the present friction loss between water particles. Practical application. Despite small deviation, Bernoulli theorem remains applicable since the percentage error was below 10%. This principle is valuable for understanding nozzle, jets, and diffuser in real-world application.
Okay, sources of error and recommendation. Human error, parallax error during manometer readings, inaccuracies in discharge valve readings, timing error and when measuring flow rates. To minimize human error, multiple group members took turns taking readings to ensure uniformity and reduce mistake. Apparatus error, improper connection between flexible hose and outlets, inadequate water level in manometer tubes, air bubbles trapped in the system. These errors were addressed by carefully following setup, procedure, and making appropriate adjustment to static pressure by manipulating the bench and discharge valve. Okay, so for the last one is conclusion and key takeaway. First is verification of Bernoulli theorems. The experiment successfully demonstrated Bernoulli equation by comparing the behavior of ideal and real fluid. The result confirms that as cross-sectional area decrease, velocity increase and pressure decrease. The second one is teamwork and organization. The laboratory session frustrated good teamwork through effective communication, equitable distribution of tasks, and punctual completion of assigned parts, enhancing the overall learning experience. For the third one is practical application. Understanding Bernoulli's principle is crucial for designing and analyzing fluid systems like nozzles, diffusers, and venturimeters used in various engineering applications. This experiment provides valuable hands-on experience in applying theoretical fluid dynamics principles to real-world situations, reinforcing the importance of both theoretical understanding and practical skill in engineering education.